Okay, great. So I would like to get back to the theme of categorification, that is replacing sets by categories and seeing how mathematics changes. But I want to talk about a pretty concrete example of it in terms of combinatorics. So in fact, quite likely for the remaining talks, I'll be talking about applications to combinatorics. Combinatorics is the art of counting things. And so you might think of combinatorics as being about numbers, but as I've already pointed out, numbers are really just decategorified versions of finite sets. So two finite sets are isomorphic if they have the same number of elements. And one thing combinatorists realized a long time ago is that they're really not, when they're counting things, they're really not really studying natural numbers, they're studying finite sets. And there's a concept of a combinatorial proof of an identity where you actually establish a bijection between two finite sets, and combinatorists like that kind of proof. But one problem with all of this is, what about fractions? So once upon a time, somebody invented fractions, and mathematics has sort of gone to hell ever since then, because we start dealing with negative numbers and imaginary numbers, and it gets harder and harder to understand what you're counting with these fancy kinds of numbers. Of course, we all try to act very sophisticated and pretend like it's beneath us to worry about such things. But I was wondering what could be like something like a set that could have a fractional cardinality. And the reason why is because if I'm trying to categorify all of mathematics and I'm strutting around saying that natural numbers are just decategorified finite sets, then the question arises, well, okay, wise ass, well, what are rational numbers, or even say non-negative rational numbers, decategorifications of? And I'm going to propose an answer to that, which is the groupoids. So a groupoid, remember, is a category where all the morphisms have inverses. In other words, all the morphisms are isomorphisms. And so what I'll do is I'll show you a concept of a cardinality, something like a cardinality for a groupoid. And it'll always make sense if the groupoid is finite, that is, if it has finitely many objects and finitely many morphisms. But sometimes it will make sense even more generally in certain cases. So let me just tell you what it is. So this concept here is called groupoid cardinality, at least that's what I like to call it. And it goes like this. So some warm-up definitions. So say you have a groupoid. So remember, that's as a set of objects. And for every pair of objects, set of morphisms. You can compose morphisms. They're associative. They're identity morphisms. And every morphism has an inverse. That's what makes it be a groupoid. So then I'll make up some terminology, which actually I've introduced earlier, but I'll remind you. So let X underline be the decategorification of X. That is, let X be the set of isomorphism classes of objects. So you say two objects are in the same isomorphism class if they're isomorphic. And this is sort of the main way that you get back down from groupoids to sets. Then, so I'll write X with brackets around it for the isomorphism class of some object. So this will be the isomorphism class of the object X. By the way, in case you're not savvy to this, people write the membership sign to mean that something is an object of a category. So here X is an object of this groupoid X. Then one thing that you can do is you can look at an object and you can look at all the morphisms from it to itself. if you're in a groupoid, all those morphisms are isomorphisms, so they're all invertible, and you can compose them, so you get a group of them. And since we're in this groupoid situation, I'll just call this aught x. So let aught x be the group of all isomorphisms from X to itself. So those are called automorphisms. So that's always a very good thing to look at. Like, right, if yeah. Thanks. Here, now the other board isn't visible, but that's okay. So yeah, so this is the group of all isomorphisms from X to X. And since X is a groupoid, that's all the morphisms from X to X. Okay, now here's the definition of cardinality. So the cardinality of our groupoid X is going to be this. I'll call it X with lines around it. So what we'll do is we'll sum up, and we'll sum up over all isomorphism classes of objects. So we'll go around looking through all the isomorphism classes of objects. So that's, I mean, X is a representative of the isomorphism class here. And what we'll do is we'll take a representative from each isomorphism class and look at its group of automorphisms and take the cardinality of that. So this is the usual cardinality of a set. And then we take its reciprocal and we sum them up. So here what I'm doing, you see, is I'm going through all the isomorphism classes of objects. For each one, I pick a representative, and I get this automorphism group. And it turns out the size of that automorphism group doesn't depend on what representative I pick. So for example, if you have a groupoid with two objects that are isomorphic, then if one of them has some automorphism, then you can always conjugate that automorphism with this isomorphism and get an automorphism over here. So like here's F inverse G, and here is, well, depending on what order you write things, something like F inverse. So the cardinality of this doesn't depend on the representative you pick. So the key point here is that objects with more symmetries count as smaller. And that may seem weird at first, but if you have done well, it is weird, okay, but it turns out to be the right thing to do, and we'll see why. But I just want to mention that, like, if you're someone who ever had to learn about Feynman diagrams and calculating stuff in quantum field theory with Feynman diagrams, it turns out that when you sum over Feynman diagrams, but if a Feynman diagram has a bunch of symmetries, you have to divide by the number of symmetries of the diagram to get the right answer. And so that's actually an example of this philosophy. So let's do some much easier examples. So for example, so here's a groupoid. It has three objects and as few morphisms as possible. So it just has the identity morphism for each object. This groupoid here is really just an inflated version of the set with three elements. So you can think of any set as a groupoid that just has identity morphisms. So this is just three. This is a picture of three. And if you work out the cardinality of this groupoid, well, you get the number 3, right? Because there's 3 isomorphism classes of objects. Each one has just one automorphism, namely its identity, and so on. So great, we can count. But the fun part happens when you have more automorphisms. So like at the other extreme, I could take an object and I could have a single object with a number of automorphisms. For example, if I do the group Z mod 3, I could turn that group into a groupoid where the group is the automorphisms of this object here. And if you see, this cardinality of this thing will be 1/3. So this groupoid here is basically just the group Z mod 3 turned in, because I can say Z mod 3 because there are not that many different 3-element groups, right? So I know it's got to be isomorphic to Z mod 3. And what I mentioned before, that if you could take any group like Z mod 3 and you can turn it into a groupoid with just one object, and it's called B of that group. So here we get 1/3. So now why? Okay, so that's how it works. And I do mixtures of these kind of examples, and it's pretty simple. So why is it a good idea? Well, first, there are a couple of basic good points about this definition, which are these. I'll write it as a theorem, but all these things are very easy to check. So one thing you can do is take two different groupoids. You can take their disjoint union. That is, you can just set them side by side and not have any morphisms going back and forth between them. And that's a new groupoid. And we write that as x plus y. And that's, in category language, that's called the coproduct of the groupoids. But disjoint union is a fine way to think about it. So that's a groupoid, and its cardinality will just be the sum of the cardinalities of x and y. And that's comes straight away from that formula of cardinality as a sum. So that's good. Any concept of cardinality should have some property like this. Similarly, given two categories, in particular two groupoids, you can form a product of them. The product of two categories is a category where the objects are ordered pairs, one from each category you're taking the product of. And the morphisms are ordered pairs, and you do composition component-wise. So this is called the product of categories, or in this case, groupoids. And you could draw a little picture of it, but it would just look like the usual kind of rectangle thing that you draw when you draw a product of sets, but with some arrows between them. And anyway, you can easily check that the cardinality of a product is the product of the cardinalities. So I don't know, I could have written the times here, but I think they teach you when you're learning math that like writing a time symbol for multiplying numbers is like only for elementary school students, and that you have to use a dot to prove that like you've made it to high school. But anyway, this looks more beautiful this way, so I think I'll regress to elementary school. So those are good. But then there's another fact that's very important, which is that there's a concept of equivalence of categories. So, and it's a bit more flexible than the concept of isomorphism of categories. Two categories are equivalent if you can find functors going back and forth, that they don't need to be inverses of each other. They just need to be inverses up to natural isomorphism. So if you go there and back, you get a functor that's naturally isomorphic to the identity. And this concept of equivalence is written like this usually. And it turns out that if two groupoids are equivalent, then they have the same cardinality. That would be super easy to see for isomorphism of groupoids, because isomorphism means that like it looks exactly alike. It has the same number of objects and so on. But you could have groupoids that are equivalent that don't have the same number of objects. So you have to work a little harder to check that this is true. So for example, here is a groupoid of cardinality 1. And here's another groupoid that's equivalent to that. So this had one object. This has two objects, but they're isomorphic to each other in a unique way. And they both have their own identity morphism as well. So these two groupoids are equivalent, but not isomorphic. And if you notice, they both have cardinality 1. Because this guy now has this, and then also this as automorphisms. So if you haven't thought about equivalence much, the point here is a very simple philosophical point. There's not that much difference between having one thing and having two things that are isomorphic in exactly one way. So like if I said, I have two daughters, but they look exactly alike, and there's like, in every single respect, any question you ask about one will be have the same answer as the other. They're always in the exact same position, etc. Well, that's a lot like having one daughter, right? So that's the idea there. And so if you ask, like, what's the cardinality of this groupoid of daughters of yours? You could say, I have two daughters, honest. But groupoid cardinality would give you the answer 1. So that's good. Well, we'll think about that. Maybe just by 2 pairs of uniquely isomorphic nappies. And it's hard to tell that from 1. So, okay. But luckily, this is purely theoretical in my case. I haven't had to deal with that. So now here's the interesting part, the really interesting part. So say you're given a set X and a group G acting on it. So one thing you can do is you can take the set and mod out by the group action, that is, form the set of orbits. And that's written as X over G. But that's not very good in the following sense. You can take the set of orbits, and unfortunately, that's not equal to the cardinality of X divided by the cardinality of G, usually. So we want to fix that, because we like to be able to divide. If you're working with rational numbers and you can't divide, you're in serious trouble. So there's a groupoid that solves the problem. There's a groupoid, which is often written X /G, and sometimes it's called the weak quotient of X by G, or sometimes homotopy quotient, or sometimes action groupoid. There are different names for it. And here's how it goes. So the objects are just the elements of X. So we don't mess around with them. But then what we do is we put in some morphisms between them. So a morphism from one element of X to, say, little x, some other element, little y, what it is, it's an element of the group G, say an element, little g of the group G, such that G of X is equal to Y. So what we're doing here is we're saying that if you have a group element that maps X to Y, we're not going to make X equal to Y the way you would do in the usual quotient. We're just going to say there's an isomorphism between them. I mean, this is a morphism, but you can see that it will have an inverse because G inverse will map Y back to X. Well, you can see it if you know how to compose morphisms. I'm going to say that, just say that composition of morphisms is done in the obvious way, and hope that you think about that and figure that out. You have to be able to compose morphisms, but there's a really tempting way to do that in this case, and it's the right way. So here is what we get then if we use this weak quotient. We get that the groupoid cardinality of this groupoid X weakly mod G is equal to the cardinality of X divided by the cardinality of G, at least when the sums converge. Before the definition of the cardinality involved the sum. That sum could wind up being infinite if your groupoid was infinite. And then here, in this case, if both these were infinite, you might get infinity over infinity. And then then I'm not making any claims about what we get. But if x and g are finite, there's no problem with that, and it always works. Let me just do an example of this theorem. So this is like a little calculation, but it's more fun to illustrate in an example. So let's take a 5-element set. And then let's get the group Z mod 2 to act on it. So the group Z mod 2, it does look like it's acting as symmetries of this line of dots. So, of course, the identity element of Z mod 2 has to map everything to itself, but the interesting non-identity element of Z mod 2 maps the dots on left to the dots on right and vice versa. And then there's this guy in the middle that's getting mapped to itself. So here, what this picture here is it's the 5-element set. I'm just going to call the set with 5 elements 5 for short. And a particular way of acting on it by the group Z mod 2. And then I formed the weak quotient of it here. Now, what's the cardinality of this guy? Someone tell me. So we go through the isomorphism classes of objects. How many isomorphism classes of objects are there? Someone be the... Yes? Oh, sorry, I couldn't see. I thought you were raising your hand, but you are, in fact, also answering the question. Yes, 3. Yeah, so these are isomorphic, this is isomorphic. So there are 3 isomorphism classes of objects. This guy has just one automorphism. This guy has one automorphism, and this guy has 2. So the cardinality of this thing is 1 plus 1 plus a half, which is what it's supposed to be. It's 5 halves. So the idea is that when you take this 5-element set and you sort of fold it in half, modding out by Z mod 2, in the ordinary way of modding out, if you did the usual quotient set, there'd be just 3 orbits, and you'd get this idiotic result that 5 divided by 2 is 3, because you weren't smart enough to know about 1/2. You weren't smart enough to know that this guy counts as half a point. But in groupoid cardinality, this point gets folded in half by this symmetry, and so it counts as half a point now. So things work out better. Okay, so that's the basic idea. Now, for something more far out, so let E be the groupoid of all finite sets and bijections between them. So this is a very important groupoid. So what's the cardinality of this groupoid? Now, this is an infinite groupoid. So the sum we're doing might not converge. So I mean, we're sort of pushing my luck here. But we'll try it anyway. So first of all, what's the set of isomorphism classes of E? Well, I've told you that that's called the natural numbers. There's 2 finite sets are isomorphic if they have the same natural number of elements. So this is just the natural numbers. And in fact, there's a famous way due to von Neumann, maybe, of thinking of natural numbers as actually being particular finite sets. And that's useful now, just to save labor. So in his approach, 0 is the empty set, 1 is the 1-element set that just consists of 0, 2 is the 2-element set that just consists of 0 and 1, and so on. So if we think about this is just cute, of course, but if we think about things this way, then it's not just that the natural numbers are isomorphism classes of finite sets, which is true, but also each natural number is a representative of that isomorphism class. So that's how I'll talk, and hopefully that's not too confusing. So like when I say 5, I mean my favorite 5-element set, the set of numbers from 0 to 4. It's just good to not have to make up 2 different notations for the number 5 and your favorite 5-element set. Okay, so then now I can do this. What's the cardinality of the groupoid of finite sets? Well, we're supposed to sum up over all equivalence classes, isomorphism classes of finite sets. So we're supposed to sum something up, but we've seen there's one isomorphism class for each natural number, so we're really just summing over natural numbers. And then what we're summing is the reciprocal of the cardinality of the automorphism group of a representative set that has that number of elements. Well, my representative set, I'm just confusing you by calling it n itself. So here n is my representative n-element set. And this is a famous group. This is called a symmetric group. It's just all the bijections from an n-element set to itself. So this is really just 1 over the cardinality of Sn, but the cardinality of Sn is n factorial, so this is E. So that's why I called this groupoid E with big capital letters, because its cardinality is E. So we found a groupoid whose cardinality is E, and this sort of gives some new light on why the number E is so important. I mean, there are lots of reasons why E is an important number, and they're all connected to each other, but I claim this is one of the more fundamental ones in the end. And in particular, this is not just like a numerical coincidence. It's also true that if you work with the groupoids themselves, a similar formula holds. So the groupoid E is actually a coproduct or disjoint union of groupoids, 1 for each natural number, because there are no bijections between a 5-element set and a 6-element set. So this groupoid, you can just chop it up into these separate groupoids, and each one of those separate groupoids is really equivalent to this weak quotient of 1 by the permutation group. That is, the groupoid of 2-element sets has a whole bunch of objects that are all isomorphic, and each one of them has an automorphism group that's Z mod 2 or S2. So this is a picture of 1 over S2 here. And so you can show that this groupoid is equivalent to this coproduct of groupoids. And you see that this formula here is really categorifying the more famous formula that E is the sum over 1 over n factorial. So what we're doing here is we're saying that this formula here with numbers is just like a pale shadow of this formula here involving groupoids. You just take the cardinality of both sides of this equation, and then you get this equation, or this equivalence becomes this equation. So that's good. That's supposed to make you happy. So now you can go on and see how much math you can categorify in this particular way. And that's sort of what I'm going to be talking about. And it'll take a little bit of machinery to get to like really exciting applications of this. But I want to introduce some of the basic concepts today. So to lead into that, you could do this, right? So if E is such a great idea, then clearly the exponential function should be a great idea too. I mean, it's sort of weird to separately study E and not the exponential function. So let's define a kind of exponential of a groupoid. So if X is any groupoid, let's define its exponential. I'll write it like exp of x. This will be a groupoid. And what it will be is the coproduct or disjoint union of a bunch of groupoids. And you can guess what they should be. I'll take the groupoid x and I'll take its product with itself n times. So x to the n for groupoids just means I sort of sketched through what the product of categories was. So you could take a product of a category with itself n times, and that's called x to the n usually. Now, the permutation group Sn acts on this groupoid because, oh, whoops, well, it does. I forgot to say something, but that's true. So the permutation group acts by permuting these factors. And the whoops part is that I meant to say that this weak quotient idea that I introduced for a group acting on a set also can be extended to cover the case of a group acting on a groupoid. So that when you do that, you can make sense of this weak quotient here. So this is clearly a nice looking formula because it's just like the usual power series for the exponential, with the number n factorial being replaced by the group Sn. So I'm generalizing the weak quotient here. So basically, if a group G acts on any groupoid, again, I guess I can't call that groupoid X anymore, so I'll call it Y. We get a groupoid called Y weakly mod G. So how does that work? Well, I don't think I want to write down the formulas for exactly how it works, but basically the idea is you take your groupoid Y and then you throw in new morphisms between objects. So when a group element maps one object of Y to another, you stick in an isomorphism between those two. So I described it in the case when we started out with a set. So there was no interesting morphisms at all until we stuck in the morphisms coming from the group action. But it's a little bit more tricky, but not terribly hard to generalize that to the case where your groupoid already had some morphisms in it, and now you're sticking in some new ones. You have to figure out how to compose the new ones you're sticking in with the old ones you already had. But you can do it, and I can give you a reference to a paper that talks about that. Anyway, in this particular case, our group G is the permutation group acting by permuting these factors here. So this is a very cool thing to think about. So for example, let's just let me just talk about one of them. So suppose, for example, our original groupoid X here that we're going to exponentiate, suppose this is just looks like this. So it's a very boring groupoid, just has two objects and only identity morphisms. So this groupoid here really is just like an inflated version of the set 2. So this is often called 2. You can, like I said, you can turn any set into a groupoid with only identity morphisms. 2 is I'm thinking of 2 as first as a number, then as a set, now as a groupoid, but it's just 2 dots, no matter how you think about it. So let's do that. So then I'll just say a little bit about like what this thing looks like in that case. In fact, I want to give these 2 dots names that let you tell them apart. So I'll make one of them be a black dot and one be a white dot. So for example, X to the 5 would have a lot of objects. I guess it would have 2 to the 5 objects in it. And a typical one would be, well, maps from the 5-element set to the 2-element set. So basically what you do is for each of your number from 0 to 5, you pick whether you want to make a white dot or a black dot. So these are the objects of x to the 5 with arbitrary choices of color. But then there will also be now morphisms in this weak quotient here. I started out with a case where x started out not having any morphisms except identity. So the only way we get morphisms of interest is by taking this weak quotient. And I already said we get those from when we have group elements mapping something to the other. So like, for example, we'll have morphisms between them. So for example, what's a morphism? Well, a morphism would come from a permutation, an element of S5. So here's a permutation. See, I guess I should make it mildly interesting here. And that will work out being an isomorphism between this object and this object. That is, the colors you can check have to go for the ride. So in other words, this is a 2-colored 5-element set. This is another 2-colored 5-element set, but they're isomorphic via this morphism. So x to the 5, what it is it's the groupoid of 2-colored 5-element sets, where the bijections have to preserve the coloring. And then you only get these morphisms when we actually start modding out by that. Then we get the morphisms. So exp of x, we're summing over all possible n. So exp of x is the groupoid of 2-colored finite sets. And color preserving bijections. When you're a real category theorist, you don't say the last part because you're forcing your listener to guess what the morphisms are. And so if I say the objects are 2-colored finite sets, why would I say they're 2-colored if I didn't want the morphisms to preserve the color? That's the attitude. It's a bit sloppy, but people do that. But anyway, so just like when you talk about the category of groups, there's a sort of obvious notion of morphism, and you probably mean that one. Okay, but then what's the cardinality of the groupoid of 2-colored finite sets? Well, you can guess. So we can push the cardinality through the sum. I showed it for finite sums. We can push it through the quotient. So what we wind up getting is 2 to the n over n factorial. In other words, we just wind up getting exp of 2, or e to the 2. So the cardinality of the groupoid of 2-colored finite sets is e to the 2. Now that was nice, but notice that was just a case where x, although I was thinking of it as a groupoid, it was a very boring groupoid. It only had identity morphisms. So it gets more interesting when you take x to be an honest, an exciting groupoid. Let me think. I think I will give the main definition of that we will be investigating in the future. I want to give another example of this, but I'll let you do an example where x is a more interesting groupoid. Then you can get a groupoid with cardinality square root of e or something like that. That's fun to do. But I want to go even more general. So more generally, this is the big definition due to Joyal, it's a concept of a species. And what it is, it's a functor from the groupoid of finite sets, which we're calling E, to the category of sets and bijections, which we call set. So what's the point of this definition? The idea is that for any set, for any finite set, you get a set, and you think of that as a set of structures of some sort that you can put on your finite set. So we call, so if I pick a set, say S, we call f of S, so that will be some set. We call it the set of F structures on S. And what they are depends on what F is, of course. But the point is, a lot of combinatorics is devoted to counting structures of various kinds that you can put on finite sets. So I looked at one example so far, the two colorings. Very baby exercise in combinatorics is to count the number of two colorings of a finite set. But there are lots of other examples, and I'll be talking about many in the weeks to come. But for example, f of S could be the set of all ways to pick a graph with S as the set of vertices. Now, there are different definitions of what a graph is, unfortunately. But luckily, that doesn't matter at all. Because whatever concept of graph that you know and love, there will be some set of graphs with S as its set of vertices. And so that will give you some kind of species. And so the F structures would just be graphs in that case, depending on what kind of graph you're talking about. And as a combinatorist, you might want to count the number of graph structures on a finite set. So that's a good thing to think about. But now what I want to point out is that you can copy this exponential function more generally. The exponential function I defined by a power series, but there are lots of interesting power series besides the exponential function, and we'll get one for every species. So if I have any species F, there's a groupoid. Right. Given a species F, I'm going to write down a power series and I'll apply it to some groupoid X. And I'll get a new groupoid. I don't want to call it F of X because that's too confusing. So I'll call it F hat of X. So what is it? I'll just define it using a power series. So I'll sum over natural numbers. And then, but remember, you can also think of these natural numbers as finite sets. So I can apply F to that finite set, that n element set, and I get here some set. And because F is a functor, it not only sends objects to objects, it sends morphisms to morphisms. So maps from the n element set to itself will give maps from this thing to itself. And there are a lot of maps from the n element set to itself, namely the permutations. And they form a group, Sn. So Sn will act on this group, on this set Fn by permutation. And then I just write the obvious thing like this. So this is just like how you would write a Taylor series of a function where the Taylor coefficients are these would be numbers. But now you see what's going on is everything has been jacked up. We've categorified. So now these guys are sets. This thing here is a groupoid, and we're multiplying it with this groupoid, and the answer is a groupoid. And this is coproduct of groupoids. But the great thing about it is that because our definitions of these newfangled objects get along with cardinality, we get this little fact that we can now, oh, sorry, let me say what the hell this thing is called before I calculate its cardinality. So I would call this thing the groupoid of X-colored F-structured sets. So there's sets that have the structure of type F on them, but also we've colored their elements with this groupoid X. I'll have to give you examples before that can really make sense. So the baby example I did of the exponential function was the case where f was just equal to 1. So there's basically nothing interesting about the f structure going on there. There's just one way to put that kind of structure on any set. The only fun came from the coloring, and I picked the case where like x was 2, and so then we got 2 colored sets.
Wait, you're saying if f is 1, then you get back to set 4.
If f of n is equal to 1
Yeah.
for each n, that's right. Because I just, oh, sorry. Whew. Thanks, Tom. Thanks. So the permutations not only act on the set of structures on the n element set, they also act on x to the n by permuting the different copies in the product there. And so I have to first take the, so Sn acts on this and we modify it. Yeah, thanks. That makes a difference. I'll give examples. I'm sort of running out of time, so I just want to point out the cool thing that you can immediately see, which is that you can calculate the cardinality of this groupoid. So it's the cardinality of this thing, but then we can evaluate that. You can push the cardinality into the sum. But then cardinality goes along well with weak quotients, and we're taking a weak quotient by an n factorial sized group. And then cardinality also gets along with products of groupoids. So you see, you can push the cardinality signs all the way in. And so what we get is the cardinality of Fn over n factorial times the cardinality of x to the n. So it's really just applying some function, which maybe I'll call lowercase f, to the cardinality of x, where this function is given by a power series, and it's called the generating function. So f is this power series here, assuming it all converges. If it diverges in a way, that's okay. You just get infinity because you're adding up non-negative numbers. So this thing has a name in combinatorics. It's called the generating function of our species. So our species gives this sort of categorified power series, but then if you slap cardinalities around it, you get a plain old power series. So the way it worked historically is that combinatorics discovered that to count things, it's really handy to use generating functions. All sorts of operations on the things you're trying to count manifest themselves as operations on the generating functions. And using that trick, you can count all sorts of things. And that's mainly what I'll be talking about next time. But this is sort of the modern outlook on that, which is that the generating functions, why are they so useful? Well, they are just sort of what shows up when you take a groupoid of sets with some interesting structure on them and then calculate their cardinality to get a number or a function of the size of x. Okay, so I'll stop there, and next time we'll do examples. Thanks. Yep.
Is the exponential of x plus y the exponential of x times the exponential of y?
I haven't thought about that lately, but is that a Zoom question or is that you? But no, oh, you're saying it as if you're. Okay, you sounded like you were saying it from someone else because you said it loud like this. I believe so. I believe so. I'd have to think about it a bit. Yeah, assuming everything converges, just to cover my butt there to make sure. But I think so. Yeah. Oh, yeah. But here everything is commutative. So for sets and for groupoids, x times y is isomorphic or equivalent to y times x. So it's commutative enough to carry out. So you could take your usual sort of power series proof of that for exponentials and just carry it through.
Is cardinality of the exponential of x the exponential of the cardinality of x?
Yeah, I should have said that. I didn't quite have time, but here I sort of showed it more generally that the cardinality of f hat of x is the generating function applied to x. So yeah. Yeah, so now you can make up now you can find all sorts of groupoids of all sorts of wacky cardinality, like cosh of 2 and stuff like that, which I'll talk about next time. Yeah. I thought there was another question lurking back there. Okay, yeah.
Are there groupoids with negative cardinality, or is there?
Oh, now what? You're not happy? I just give you all the positive rational numbers and you're still not satisfied. You're happy but not satisfied. Yeah, okay. You'd better be happy. Yeah. Okay, but if you're happy, then it's yeah. So you're in luck. The person sitting directly in front of you has generalized the cardinality of groupoids to the cardinality of categories, some class of categories. And then it turns out you can often get negative cardinalities showing up as well. Yes. So you should ask him for some juicy examples of that. But so those are sort of more tricky. One place that they sort of show up is there's a thing that you do in combinatorics called Möbius inversion, which is sort of some kind of stuff connected to the inclusion-exclusion principle, where you're counting a set by adding and subtracting. And if you think about that enough, you get pulled into wanting to really understand the negative numbers in combinatorics. And then Tom has shown that you can understand Möbius inversion using cardinalities of categories. Yes.
And there's another story there, which is that you can turn any category into a topological space and take a classifying space, and the cardinality of the category is equal to the Euler characteristic of the classifying space under certain conditions. So, for example, if you take the category with 2 objects and 3 parallel arrows from the first to the second,
Great.
the classifying space is a pair of the weights of 2 circles. That has negative Euler characteristics, and so your category has negative Euler characteristics.
Yeah, so Tom was talking about this category here, for these identity morphisms here. So if you think of that, these are the identity morphisms you should think of as being very tiny. So if you think of that as like a letter theta, and you say, what's the Euler characteristic of that? You get -1. And then so what Tom is saying is that the cardinality of this category is also -1. By the way, one really cool thing is that the Euler characteristic of this space is 0. And I don't think that's a coincidence, actually, because so why did people call 0 this thing? Why did they make up the name 0? I think the reason was basically that you want to draw something, but it has to be nothing. So you draw it and then you remove all of it, but there's still the edge left. So this is like nothing with a frame around it so that you can tell that it's there. And then it turns out that the Euler characteristic of that is 0 because you started out with a thing of Euler characteristic 1, namely a point, a fat point, a disk, and you removed something of Euler characteristic 1 from it, and so you're left with something of Euler characteristic 0. So I don't actually think it's a coincidence. Yes?
The exponential of groupoids is being defined.
Uh-huh.
So I get the function category of x to
No, it's not, unfortunately, or whatever. That's why I called it exp instead of e to the x. It is when x is just a set. So like exp of 2 is really just e times e. It's the that was the groupoid of 2 colored sets, but that's equivalent to the groupoid of pairs of finite sets. But when you have a groupoid with more interesting, when x has more interesting morphisms in it, that is when it's not a discrete groupoid, then I don't think that's true.
Use a category of elements that broken different ways.
Can you say what's the category of elements of what?
You take the function from finite sets to sets of species that sends n to x to the n. It's the category of elements of that.
Huh. Okay, I'll have to think about that. But I knew. But anyway, to your original question, the answer was no, and alas, but no, yeah. Okay, thanks. I'll see you around next week, I hope. Sure.
maybe one of the
Yeah.